Welcome to the new era of video creation with Bayo Z8. Today we will discuss what is the difference between L1 and L2 regularization? What is the difference between L1 and L2 regularization? And how do they impact model training and performance? Regularization is a technique used in machine learning to prevent overfitting, which occurs when the model learns the noise in the training data rather than the underlying pattern. Overfitting leads to poor performance on unseen data because the model becomes too specialized to the training set. To address this, we add a penalty term to the loss function that discourages the model from assigning excessively large weights. Regularization helps models generalize better. There are different types of regularization, but L1 and L2 are the most popular ones. Both methods aim to penalize large weights, but do so in different ways. The choice of regularization can significantly impact model training and performance. L1 regularization, also known as lasso, least absolute shrinkage and selection operator, adds a penalty term to the loss function based on the absolute value of the weights. This makes L1 regularization particularly useful in feature selection, as it automatically removes less important features. However, it can lead to a less stable model when the data is noisy and may result in underfitting if lambda is too large. L2 regularization, also known as ridge regularization, adds a penalty based on the square of the weights to the loss function. In this case, the penalty increases with the square of the magnitude of the weights. Unlike L1 regularization, L2 does not drive weights to zero, but rather shrinks them towards zero. This discourages the model from relying on overly large weights, which helps prevent overfitting. L2 regularization tends to preserve all features in the model, unlike L1, which can eliminate features altogether. As a result, L2 is often used when the goal is to reduce the influence of certain features rather than discard them. While L2 regularization usually results in smaller weights, it does not perform feature selection as L1 does. The key difference between L1 and L2 regularization lies in how they affect the model weights. L1 regularization tends to create sparse models, meaning that it can eliminate features by setting their weights to zero. This makes L1 a great choice for feature selection in cases where only a subset of features are expected to be relevant. L2 regularization, on the other hand, shrinks all weights towards zero, but it does not eliminate any features. It's particularly useful in situations where multicollinearity is a problem, when multiple features are highly correlated, as L2 helps to reduce the effect of correlated features without eliminating them entirely. L1 regularization can result in simpler, more interpretable models because it forces some features to be exactly zero. In contrast, L2 regularization is better suited when the goal is to reduce the impact of large weights without necessarily discarding features. The regularization strength is controlled by the parameter lambda, which determines the magnitude of the penalty added to the loss function. The choice of lambda is very important for controlling the bias variance trade-off. A large value of lambda imposes a strong penalty on the weights, forcing them to be smaller, which can result in underfitting. The model fails to capture important patterns in the data. A small value of lambda leads to weaker regularization, and the model may overfit the training data, capturing noise and irrelevant details. Typically, lambda is tuned using cross-validation to find the optimal balance between bias and variance. This ensures that the model generalizes well without overfitting or underfitting. L1 regularization is particularly useful in situations where sparse data is expected. When you believe that only a subset of the features are important, L1 regularization can help identify those features by driving the irrelevant ones to zero. Feature selection is a priority, as L1 forces certain features to be discarded entirely, i.e., their weights become zero. This makes L1 regularization useful when you want to automatically identify a smaller, more relevant subset of features. The interpretability of the model is important, as the resulting models from L1 regularization tend to be sparser and more easily understood, which is critical in some applications where understanding the decision-making process is necessary. L2 regularization is preferred in scenarios where multicollinearity is an issue, as it allows correlated features to contribute without completely eliminating them. By shrinking weights, L2 regularization reduces the influence of highly correlated features. Stable models are desired because L2 does not eliminate features, but instead ensures that the model doesn't rely too heavily on any single feature. This can help produce models that are more stable during training and testing. Preventing overfitting while maintaining all features in the model is another reason L2 regularization is often preferred. It provides a smoother and more continuous reduction in the magnitude of weights. ElasticNet regularization combines both L1 and L2 regularization, offering the best of both worlds. It allows for feature selection while also controlling for large weights, which helps with model stability. It is particularly useful when dealing with highly correlated features where L1 alone might discard some useful features, or L2 might not effectively reduce their influence. The formulation of elastic net includes both L1 and L2 penalties, making it a more flexible approach that can handle complex data sets. Elastic net is a good option when neither pure L1 nor pure L2 regularization is ideal for the given dataset. It provides a balanced approach to regularization. In summary, L1 regularization is best for feature selection and interpretability, as it eliminates irrelevant features and leads to sparse models. L2 regularization is better suited for stabilizing models and reducing the impact of large weights, especially when multicollinearity is a concern. Elastic net provides a middle ground, leveraging both L1 and L2 to create a more robust regularization scheme. Finally, tuning the regularization parameter ln lambda is critical for ensuring that the model generalizes well and does not suffer from overfitting or underfitting. Regularization plays a pivotal role in developing robust AI models that perform well on unseen data. Choosing the right technique, L1, L2, or elastic net, depends on the data characteristics and problem at hand. Regularization helps us balance the complexity of the model while minimizing overfitting. Experimenting with different regularization techniques and tuning lambda appropriately is key to improving performance. Stay up to date with the latest research and advancements in regularization techniques to keep your models state of the art.